Alright guys, let's get started with the algorithm for insertion sort, and I will also be explaining how it exactly works, and we will then do its performance analysis in this video. Alright, very first let's define our function and pass the argument for our array, and then let's define the first loop. For I in range, we will start from our second element since the first one is already considered as sorted, and then pass the length of the array. Our first loop is here done. It basically controls number of passes, and then we will define our key, which we'll use to compare with the rest of the previous elements. Which each iteration our key will change, and then we will need j in order to conclude the number of possible comparisons. Now we will write another while loop, and make sure that you are using brackets, otherwise Python will raise error. And then we will compare that our key is less than error of j. And if indeed the two conditions are met, we will basically move the element to the right side. And then reduce the value of j. And by the end of the while loop, still remaining in the for loop iteration, we will add j plus 1 and assign it the value of the key. Once we are done with this and we are out of the loop, we will just return our array. Now as we can see, our function is mostly done. Let's create a random array and let's sort it out. I think this is good to go. And then we will move towards our, let's just create a variable. And call the function insertion sort and pass on our array variable, list, whatever you call it, and then let's print the sorted array. Let's see, it should work as expected. As you guys can see, we have sorted this into ascending order, and now if you want this algorithm to work in descending order, all you have to do is change this relation operator here, and as you can see, now we are doing it in descending order. Now we are going to move towards the performance analysis phase of insertion sort and discuss how it is exactly working there. But before that, allow me to explain one more thing. There's this line right here, control the number of passes, while this gives us the value to compare with. Now here we get the number of comparisons possible, and we only perform the comparisons when both of these conditions are met. Basically we are just transferring the element to the right side if the element on the left side is greater than the element that we are currently having, and our left side is considered sorted always. That's why we start with the first index and not with the zero index, right? Since array start with 0 in Python. Alright, let's start with the performance analysis of insertion sort. First of all, I would like to clarify one thing, that insertion sort is basically dependent on both sides of the problem and value of the problem in terms of time complexity. When it comes to deciding the time complexity of our problem, we will focus the size of the problem, which is n, and the value of the problem, which is the elements in which order they are arranged and how much sorted out they already are. Now, let's come to worst case. For the worst case, or which you may also known as upper bound, it has order of n square, because let's see here. For the first loop, obviously you will have n passes, and that is from 1 to n, that is n minus 1, and then one case for failure run. Then it makes it n number of times. And then we will have similarly for these two lines of code, they will also run n times. As for this one will run for n to the power 2 times, and so will the else of the code which comes under this iterative loop. This line will only run one time, and as we can already see, the highest degree order is n square. So the worst case is order of n square, and as for the best case, it is order of n. Now you may wonder why it has order of n unlike bubble and selection sort. That is because this line here won't run unless both of these conditions are met. And if the array is already sorted, then none of these will meet the conditions, and we don't need to actually run this line, which makes it to the order of n only. And this is one of the reason insertion sort is preferred over even merge and quick sort in case of small arrays or list. Now for the average case, it is the same as the worst case, order of n square. Now let's talk about some of its characteristics. First of all, it is an internal algorithm and it can be seen in the code itself. It is a comparison based sorting algorithm, and it is polynomial, that is order of n square. It is no, actually let me fix this. Insertion sort in general is stable. All right, stable, that is the relative order of two elements will remain same unless and until there is a difference between them. But if I had equal to here, it becomes unstable algorithm because then the relative elements will also keep changing. I hope you understood that statement. You can also try out definition for being stable and unstable as well if you have any confusion. Now let's see an example for this line of code. All right. Uh, we have our array here, and in the past one we have the value of I2, that is our key will be 63, and we will check if 63 is less than 29. It is not less than 29 and nothing will happen, that is this loop will not run. For the next pass, we will have I is equal to 3, that is our key will be 7, and since 7 is less than 63, we will get 63 in place of 7, and 7 will remain in the key. Then we will check if 7 is less than 23, and we will get 23 into the second position, and then we will assign this position as the key where 7 will be here, and it will stop once j reaches equal to 0, because j has to be greater than 0 in order for the while loop to be running. Now we will go towards our third pass, and as we can see, I is equal to 4, key will be 71, and it is already not less than 63, and hence our while loop won't run. For the fourth pass, as we can see, the following case scenario will happen, as 55 will be the key and 55 will be less than 71, 63 but not than 29. Hence 71 will move forward, so will 63, and in place of 63 we will assign the key that is 55. And then in the final pass 21 will be our key, and as we can see, this of these scenarios will happen, and by the end we will have our final output, which is an ascending sorted array. So this was insertion sort. I hope it is clear to most of you. We have done our time complexities. We have seen our different cases. We have understand why insertion sort is preferred over merge and quick sort, even in for shorter list and arrays. You can note this thing though. And then we have seen different type of characteristics of insertion sort. I hope you have understand the algorithm. And remember, if you use equal to then you can write here unstable. Otherwise, the relative values will be the same and it is be considered stable. Usually consider insertion sort as stable. Now that was all for today. Thank you. Goodbye.